Hi everybody, it's Ajanette and I am going to be doing your chapter 5 lecture with you. So let me go ahead and share my screen, and then I am going to open our document, and here we go. Okay, so this module is going to actually introduce us to inferential statistics. So far we've learned some kind of basic information about statistics in module 1, learned the difference between inferential and descriptive stats. We've also looked at different types of data, and in module 2 we studied descriptive statistics, including frequency, tables and graphs. We also then discussed measures of central tendency and measures of variability. Our measures of central tendency tell us how similar data is within a data set, and our measures of variability are measures of dispersion, or how different or far apart the data points are within a data set. And our measures of central tendency include the mean, which is the average, the mode, which is the most frequently occurring, and then the median, which is the midpoint, the point at which 50% of the data lies on one side and 50% lies on the other of a distribution. Furthermore, we learned measures of variability, including our range, which is the distance from our highest point to our lowest point in our data set. We've also learned about variance and standard deviation, where variance is looking at how far apart the data points are for one another, and the standard deviation is looking at the average distance from the mean. And so we are now going to use all of that information to discuss z-scores, and z-scores are a technique that we can use to answer research questions to see whether or not we are significantly different from the mean. And we can kind of look at a z-score and immediately see the relative location of any score within a data set, okay? So when we talk about inferential statistics overall, we know that when you have a population such as, all college students, there are literally thousands of samples that can be drawn to study behavior among college students. And that is the case. You can pull multiple samples to study any given population. And as researchers, we try to make sure our sample is as representative as possible in order to ensure that the conclusions we draw are valid. But we need to make sure that we're understanding kind of how those samples relate to one another, whether the patterns we're seeing in one sample is consistent with patterns that we're seeing in other samples. We also need to know how those samples relate to the population. Are they in fact reflecting what's happening in the population? And then we need to make sure that we're looking at representative samples, because if you're drawing conclusions from a sample that really doesn't look like the population, then it can invalidate your conclusions. So things that we need to really understand as the foundation for this chapter is the normal curve. And we did talk about this early on, but we'll refresh a little bit in this early on in this chapter. Additionally, we need to know how that normal distribution works in terms of z-scores and really standardizing any variable using z-scores. And I think I have a sneeze coming on. Excuse me. Thank you. Okay, look, thank you, as if you just said bless you. But excuse me. Anyway, we're going to study something called the central limit theorem. And the central limit theorem is really the underlying mathematical theory that's the foundation for the normal distribution curve, where most of the scores pile up around the middle and then evenly taper off on either side. All normal distributions are symmetrical. Not all symmetrical distributions are normal. You'll remember me saying that in chapter 1 lecture, but all normal distributions are symmetrical. So a normal distribution has very predictable patterns, and the central limit theorem allows us to make those predictions. It's been tested and proven multiple times with literally thousands and thousands of data sets. And so we rely on that as a foundational theorem and concept for inferential statistics. And so when we're looking at a normal distribution curve, as you see illustrated here down at the bottom, this is an example of central limit theorem that suggests that your data is going to pile up. The majority of your data points are going to pile up here in the middle, right? They're all going to be in the middle. And then it's going to kind of taper off evenly on both the left and right side of the distribution. This midpoint for a normal distribution, a perfectly normal distribution, your mean, median, and mode are all equal to one another. So in an IQ distribution, let's say, we have the mean at 100, and the mean, median, and mode all are 100. So the average IQ is 100. The mid IQ in all the IQ data, the midpoint is 100, so that 50% of the population has above 100 and 50% has below. And then the most frequently occurring IQ score in the distribution is 100. So that midpoint, that peak of a normal distribution represents the mean, median, and mode that are all equal to one another within a normal distribution. That's really powerful. That allows us to draw some really, really important conclusions from it. It anchors us so that we can evaluate and analyze any point relative to the rest of the data set. Now, when you start out with a really small sample, you are less likely to have a normal distribution. So the thing here is, I have a population, I sample, I randomly pull out 100 people, and I'm going to now measure those people's IQ. And if I only pull out 1 or 2 people in my sample, it's not likely that they're going to match up with the patterns that I see in the corresponding population, right? So the bigger the sample that you pull, the more likely it is that you're going to have a normal distribution. And our rule of thumb is usually 30. We need about 30 people in a sample before our distribution starts to normalize and approximate the population. So samples smaller than 30 are not as reliable because our data is not as likely to be a normal distribution, and that normal distribution is the basis on which we really use inferential statistics. So we want to do everything possible as researchers to try to work within normal distributions when we're talking about parametric statistics, okay? So when you are looking for, when you're working with a normal distribution, the same patterns that you see on the right, because it's a symmetrical distribution, should also be occurred on the left. So if the standard deviation is 15 points above the mean, it's also going to be 15 points below the mean. So everything's duplicated on either side of the mean or the midpoint. And that midpoint, because the mean, median, and mode all equal one another, that's a really good kind of anchoring point for us to see this is a reasonable estimate for any sample or population, I shouldn't say sample or population, any score in this data set. This is a really reasonable estimation of that because it represents kind of that measure of central tendency, that average, right? And what we find in normal distributions is that most scores, they kind of hover close to that midpoint. So 75% of your scores fall within one standard deviation above or below the mean. And 95% of the population, I think I said that wrong, 70% of the population falls within one standard deviation, 95% approximately falls within 2 standard deviations. And inferential statistics are used to determine, are you kind of within what's expected within those those 1 or 2 standard deviations? Or are you in the critical regions? Are you in this point that says you are significantly different than the rest of the group? If we know that most scores cluster around the middle and you don't, you cluster way over here, there's something uniquely different about you, and you are said to be statistically different from the mean or from the groups, okay? So because of this normal distribution, we can kind of compare groups to one another. We can compare a single score to the rest of the group. I can say, how smart are you relative to the rest of your family? I can say, how good are your scores, test scores, relative to the rest of the class? I can do that very quickly by looking at a normal distribution curve and seeing where you fall within that curve. And z-scores allow us to do that, okay? So it's not advancing the slide. There you go. Standardization, z-scores are in fact a standardized score, and they allow us to make those comparisons based on those predictable standard patterns that can emerge. They very much are based on a normal distribution. And so when we talk about standardizing a data set, we're really converting the original raw scores into standardized scores that we can use as easier figures that we can talk about, that we can calculate, so we can make meaningful comparisons, but they're representing a percentile of the data. If you have a z-score of 2, you are typically in the upper 95%, 97.5% or so of the data, and everybody is below you. So they let us see where you rank relative to the other scores in that distribution. It also allows us to look at an individual score, and within that normal distribution where we know the mean and the standard deviation and the percentile, we can exactly and immediately know where that individual score falls in that distribution. So it helps us to kind of visualize a distribution. And why do we need it? It's really important because it allows us to make comparisons between 2 different sets of data and two different scales of measurement even. So let me give you a great example. Anybody travel to a foreign country, have a passport, travel internationally? Okay, I haven't been many places. I've been to Cancun, and I've been to Canada in various places, but I really haven't traveled far away. But that being said, we know that there's different currencies depending upon where you go, right? And let's say in China, where there's a yen, and then in Mexico, there's pesos, right? And I want to buy a CD in China, and I'm buying, you know, I'm a collector, so I'm also buying a CD in Mexico. I want to know, where am I getting the better deal? Mexico or Chinese? This is in or China. This is in pesos and this is in yen. How do I know which one's more affordable? I convert them both to US dollars, right? US dollars are a standard means of me being able to compare those 2 different scales, those 2 different prices. I convert my pesos to dollars, and I convert my yen to dollars. And now when I have that standard comparison, now I can say which one's more expensive and which one's more affordable. That's what the z-score is. The z-score is that US dollar. It's that standard benchmark. So we can convert scores, distributions, into z-scores. And as soon as they're both converted into z-scores, I can make comparisons. And I can say, based on the patterns that I know about a normal distribution, because a z distribution is in fact a normal distribution, then I can see, well, where is this one on the distribution and where is this one on the distribution? So I can make comparisons between those 2 scores, okay? So they're really powerful for us as researchers. And when we go on we'll actually use them to test hypotheses, to test research questions. So I want to, before I get into this, I'm gonna stop sharing for a second, and I want to go into my whiteboard because I do want you to just kind of get this normal distribution ingrained in your mind. And I'm giving you estimates right now, but ultimately we're going to get to the precise numbers at the end of this chapter. So I'm going to draw a normal distribution and just pretend with me that my drawing is precise, okay? It's not, it sucks. I'm not an artist, okay? And so this is a normal distribution where we have the exact midpoint or that exact middle is the mean, median, and mode. And for just my benefit, we'll say this is an IQ, okay? Well, let me erase that. This is going to be the normal distribution for IQ, okay? So I want you to see that the mean for IQ, this is meant to be a mu. I didn't do a good job on that, sorry. But this is meant to be a mu. Mu equals 115. And because I'm using a mu, it's a symbol for a parameter. So I know I'm talking about the population of IQ scores, okay? Mu, or excuse me, I even did this wrong, I'm sorry. The mean is not 115, the mean is 100, I'm so sorry. Okay, your mu is 100. And you actually have a standard deviation. That's the average distance from the mean, as we learned about in measures of central tendency. Your standard deviation, as represented by theta, it, excuse me, I'm choking, is 15. Okay, so that means that when we look at one standard deviation above the mean, then this would be 115 because it's 100 plus one standard deviation equals 115. And this point over here would be 100 minus 15, which would make it 85. So this is one standard deviation. And then a second standard deviation, we would add another 15, so that's 130. And we would take away another 15, and that's 70. Because remember, to the left, it's declining, and to the right, it's increasing scores, okay? So what we know about normal distributions based on the central limit theorem, without even knowing anything about the data, if it's a normal distribution and we know that a sample size of about 30 is going to approximate a normal distribution. And so what we know about from the central limit theorem about a normal distribution is that about 70% of the population falls within one standard deviation of the mean, meaning that on average, 70% of the human population has an IQ ranging from 85 to 115 within one standard deviation below or above the mean. But the average IQ is 100. We also know that within two standard deviations, about 95% of the population falls within two standard deviations. And that means that what's left over here represents about 5% of the population. So I'm going to take that 5% and divide it in half, because half falls above and half falls below. So if I add up my 95, right, in all of the middle, and then I add up my 2.5 on the end, I have a total of 100% of scores. Now I can break this down further, and I can break up this 70% into 35% here and 35% here, right? And then if I know that from here to here equals 95%, and I've already taken out 70%, that means these two chunks right here and here are the other 15%. Yeah, the other 15%. And so I can take those and say that's about 7.5, and that's about 7.5. And then, does that work? Am I doing that right? 15%, 95, 70, 15. I thought I was doing that right. Yeah, that's right. Because then it's 10, 80, 90. No, I'm missing something. Okay, forget my numbers. I think it's 12.5. I think I'm missing something. It's 20. It's 20. Okay, so here, I'm not a mathematician, right? Here, let me erase this. Oops, I erased. Okay, let me just erase all of it. And I'll start over. Because it is unfortunately, it erased my normal distribution instead of the numbers. Okay, so I said one standard deviation's about 75%, or excuse me, about 70%. That would make this 35 and 35, right? And then the next standard deviation is in between the two of them, that's about 95%. So if I take 95% divided by 2, right, that's going to be, this is going to be 2 goes into 9 4 times, and it's going to be about 47%, right? 35% is already taken up right here, so that leaves me about 12.5%. And these chunks, as I mentioned, this would be about 2.5%. So if I add up all of those scores, 2.5 and 12.5, that's 15, plus 35 is 50, same on the other side. So this is 50% of the scores, and this is 50% of the scores, right? And we know that this is our mean, our median, and our mode, okay? So our midway point equals, are all equal to one another in a normal distribution. So it is exactly the point at which half of the scores lie on one side and half of the scores lie on the other. Okay, now let me tell you why this is magical. Because I know that, right? And I know that our mean IQ is 100, right? And I know that our standard deviation is 15. So I know this is 115, and I know this is 85, and within 2 standard deviations, it's 70 and 130, okay? So I know that. And then I know that anything above 2 standard deviations establishes what we call a critical region. And what we're testing in inferential statistics is, are you in the critical region, right? You have less than a 5% chance of being in that critical region. Most people are gonna be right here in this area. 95% of the population is gonna be in the area within 2 standard deviations of the mean. But only 5% of the population is in these critical regions. So what we're testing in inferential statistics is there a statistically significant difference? Are you in the statistically significant critical region? Does that make sense? Probably not, but remember, I'm planting seeds, and we're gonna water those seeds as we go, okay? So hold this in the back of your mind as we continue on in the lecture, and then I'm going to bring in some new stuff and overlay it right on top of this, and hopefully some dots start connecting for you, okay? So I'm going to stop sharing for a second, and I'm going to go back and I'm going to share so we can start going back to the lecture, okay? So Z-scores are they're a standardized score, and they allow us to look at the exact location of a score relative to the rest of the distribution. So we can see where it stands in a distribution without even seeing the distribution. All we have to do is know the z-score. And it tells us specifically, the z-score tells us the number of standard deviations that that score is above or below the mean. So we start out with a raw score, our own IQ, and we can convert it to a z-score, and that tells us where it falls. Or we can start out with our own exam score and say, well, how did I do relative to the rest of the class? Well, I can convert your score to a z-score, and then instantly you'll see that you either did better than most of the class or you didn't, okay? So we always start with a raw score, which is your actual original data that we collected from you. It's the actual numbers that we got when we asked you or when we studied you, tested you, measured your height, whatever we're studying. It's the actual data that we got. And then we can mathematically convert it to a z-score. Using z-scores allows us to standardize an entire distribution. It allows us to, just like we talked about with the pesos and the yen, it allows us to make comparisons between two completely different distributions because we can convert any distribution to a z-score. And it tells us the exact location of any given score within that distribution. So it's a really important tool in inferential statistics. So here's an example of how we might use it. We might want to say, okay, here's one distribution of scores for an exam that you took, let's say in, let me see, what do I say in here? It doesn't say. Let's say chemistry, okay? So A represents a chemistry exam and B represents a psych exam. And here you got a 76, right, on both exams. But I still want to know, how did you do relative to the rest of the group? Is a 76 good or bad? You might think it's automatically good when you just look at, oh, out of 100, well, hey, I guess that's good. But it depends. Well, how did the rest of the class do? If the rest of the class bombed it, then I'm loving my 76. But if the rest of the class was getting, you know, 90s, then I'm not loving it so much, okay? So I want to look at where that falls within a distribution. And let's say in the first chemistry exam, the average score was a 70 with a standard deviation of 73. That means that you got, or excuse me, with a standard deviation of 3. That means that most scores are going to fall within 67 and 73 because they fall within one standard deviation. And 95% of scores are going to fall between 64 and 76, right? So hey, look, I'm right on the verge of being in that top percentile, that top 97.5%. That's pretty good. That's rocking it. But in my other exam, my psych exam, well, maybe my 76 isn't so hot because my average was a 70, standard deviation was a 12, which means that 70% of people fall within one standard deviation, so they're going to range between 82 and 58, right? And I'm a little bit above the average, but not as much as over here, right? So I did way better on this exam, even though I got the same score, than I did on this exam, just based on where I'm at relative to the rest of the distribution. Okay. So give me just a second. Okay, sorry, my kids came in for just a sec. So I'm going to go back to sharing my screen. I'm going to share the whiteboard for just a second. And remember how I said that I would come back to this, and I said that the peak point of a normal distribution, the mean, median, and mode all equal one another. And I said that about 70% of scores fall within one standard deviation, and about 95% of scores fall within two standard deviations. Well, interestingly enough, this normal distribution is also the z-scores. So for a z distribution, Your mean and median is always 0. I think I'm going to choose a different color so it stands out a little bit more. I'm going to say green. Your mean and your mean is always 0 and your standard deviation is always 1. Meaning that at 1 standard deviation, it's 1. At 2 standard deviations, it's 2. At below 1, right, because I'm now moving downward, it's -1 and it's -2. Remember that our definition of z-score said it's a standardized score that equals the number of distributions above or below the mean. So this tells us that the original score is 1 standard deviation above the mean. This one says it's 2 standard deviations. This is it's 1 standard deviation below the mean. And this tells us it's 2 standard deviations below the mean. So when it's a positive number, it means it's above the mean. And when it's a negative number, it means it's below the mean. So a z-score has a couple of different components, right? It's telling us the direction and the magnitude. So it's telling us how many standard deviations above or below the mean. And the number itself is what tells us the magnitude, which tells us how many standard deviations above or below the mean. And the plus or minus tells us whether it was above or below. Make sense? And so all normal distributions, or excuse me, all z distributions are normal, okay? And so we can convert any set of scores to z distributions based upon this standardization process. And it provides us a really effective means of comparing scores in 2 different distributions. So take, for example, I'm going to stop sharing this, and I'm going to go back to sharing my slideshow. Take, for example, this right here, right? I am seeing a score of a mean of 70 and a score of 76, right? So if the score was 70 and this is a standard deviation of 3, then I know the next score was 73, and I know the next score for the 2 standard deviations was a 76. So I know this 76 score is equal to a z-score of 2, because it is exactly 2 distributions, 2 standard deviations, excuse me, 2 standard deviations above the mean, okay? And I know it's a positive 2 because it's greater than the mean, not less than the mean. Now over here, I can figure out your z-score as well, because I know the z-score, or the standard deviation was 12, so z-score of 1 is going to be equal to 82. Well, you had a 76, which is exactly halfway between the mean and the first standard deviation, or a z-score of 1, meaning this z-score is going to be 0.5. Make sense? Okay, let it sink in a little bit. We'll do more. We'll do more practice. Okay, so the 2 parts of the z-score that I noted are going to be your sign as being positive or negative, meaning it's above the mean or below, and the magnitude, telling us how many standard deviations above or below the mean, okay? The magnitude, again, is telling us if it's a 1, that it represents 1 standard deviation above. If it's a 2, it's 2 standard deviations. If it's a 3, it's 3 standard deviations. If it's a half, it means it's a half a standard deviation. If it's 1.5, it's 1.5 standard deviations. Make sense? Okay. And it can be anything in between, because they can be broken down into fractional parts, okay? Okay. Come on. Okay. So when we're looking at a z distribution curve, we know that that midpoint, that mean, median, and mode is going to be 0. Your mean is always 0. In a z distribution, the mean is always 0, and the standard deviation is always 1. No exceptions. The mean is always 0, and the standard deviation is always 1. And that allows us a standard way of comparing. So I can just know your z-scores, and if I know that you did a half a z-score above, or your z-score was positive 0.50 compared to 2, I know that you did way better on the 2 exam than you did on the 0.5, okay? So when I'm looking at negative numbers, I know you did worse than the mean, but when I'm looking at positive numbers, I know you did better than the mean. The question is how much better or how much worse, right? Okay, so closer to the mean is going to be smaller scores, and the further away from the mean, you're going to have larger z-scores. So when we're looking at let's look at a raw score of 76 and let's calculate the corresponding z-score. I already figured that out for you, where I'm telling you that, where I'm telling you that I know that this is going to be 2, right? Because it's 70, 73, 76, because it's 70 plus our standard deviation equals 73, plus another standard deviation equals 76. So it's exactly 2 standard deviations above the mean, so it's a positive 2. Over here, I know it is above the mean, so it's positive, but it's not a full standard deviation. It's the exact halfway point before you get to a full standard deviation. So therefore your z-score is 0.5, okay? And then it's asking what would your z-score be if your score were exactly equal to the mean? It would be 0, because the mean of a z distribution is always 0, okay? Okay, now you can figure that out logically, or you can plug it into a formula. So here's our formula for our z-score. First, we're going to calculate that deviation from the mean, same as we did in calculating variance. Remember, we looked at how much does x deviate from the mean, and then we squared it, and then we summed all of those, and that was our sum of squared deviations. And we're going to divide by our standard deviation. So it's x minus your mean divided by your standard deviation. That equals your z-score. So you can figure it out logically by drawing out the graph that I gave you, or you can figure it out mathematically. When the numbers are easy, sometimes you can just visually see it. But when the numbers are a little bit more complicated, then often you will need to apply the formula. So I'm going to actually have you do a learning check. So just go ahead and hit pause and then work through these answers and tell me, what would the z-score be if you had a raw score of 130 and you had a mean of 100 and a standard deviation of 10, okay? I want you to figure that out. So just hit pause, and when you're ready, we'll come back together, okay? Look through these answers. And I'm just gonna jot them down so that I can actually go back to our whiteboard. Okay. Okay, so I am going to go ahead and just show you the first one. So I'm going to stop sharing. I'm going to go to my whiteboard now. And let's figure this out, okay? So I have a distribution. Let me go back to black. I have a distribution where our mean equals 100. And our standard deviation equals 10, which means I know the next score would be 110, the next score would be 120, this score would be 90, and this score would be 80. Because I'm going to take my mean plus 10 equals 110, plus another 10 equals 120, right? And then on the left side, I'm going to take my mean minus 10, and I'm going to come up with 90 minus another 10 equals 80. So these are my raw scores that would correspond to this distribution. Now I can, if it's a normal distribution, I can lay the z-scores right on top of this, right? And I can say this z-score would be 0, this z-score would be 1, this z-score would be 2, this would be -1, and this would be -2. And this particular example is telling you you have a raw score of 130. So what would your z-score be? Well, we haven't gone far enough, right? We need another standard deviation to get to your range. And so that is equal to 3 standard deviations above your mean. So that would be 3. Make sense? Okay. For those of you where it doesn't make sense, keep in mind you can always fall back on the formula if it doesn't make sense. For me, I like to visually see it. So I recommend that as a tool, but let me make sure. It's freezing up on me, just a second. There we go. Sometimes Zoom doesn't work well. Yeah, sometimes Zoom doesn't work well with the PowerPoints, and so especially if I launch it into full view. So I might just leave it out of full view for a second, okay? So again, if visually you're not seeing how it lays out geographically on a distribution, then you just plug the scores into the formula here, right? And so we could say z equals 130 minus 100 divided by 10. So it's 30 divided by 10, z equals 100, okay? And that would get you to the same point where I actually had you at. Oh, I wasn't sharing my screen, so you guys don't know what the hell I'm talking about. Let me go back. So I can plug in the data into the formula where z equals x minus our mean divided by our standard deviation. I knew my raw score was 130, my mean was 100, and my standard deviation was 10. So I can say 130 minus 100 divided by 10. That means 30 divided by 10 equals 3. So z for a 130 score, based on the fact pattern we were given, the z-score would equal 3, okay? And if I take you back to our original whiteboard, we already knew that it was 3, right? Right down here, we knew that it was 3. So z equals 3. So every raw score has a corresponding z-score. If someone scored 110, their z-score would be 100. Someone scored 120, their z-score would be 2. Their z-score would be 1, not 100. If someone scored 115, right in between, their z-score would be 1.5, right? If someone scored a 90, their z-score would be -1. Someone scored an 80, that's 2 standard deviations below the mean, so that would be a -2. Someone scored a 70, that would be a -3. And we could go on. If someone scored a 60, their z-score would be a -4. We could go on and on and on, okay? Make sense? Perfect. Okay, so I'm gonna go back to our PowerPoint. Okay, so here we're at, here's the formula. You were doing your learning activity, or excuse me, your learning check. So let's look and see if you got the answers right. You can just plug in to get your z-score. Hold on, I think I'm at the wrong one. Here we go. You can plug in to get your z-score, which z equals 130 minus 100 is 30 divided by 10 equals 3, okay? And then this one over here, we have a mean height of a population of sophomores. So our mean is 64.886. That would plug in right here to, oops, excuse me. That would plug in right here. And my standard deviation is 4.086, which would be my denominator. And I'm saying I have a sophomore who's 70 inches, so that's my X value. What's the Z-score? 70 minus the mean, 64.886, divided by the standard deviation was 4.086. So the Z-score that corresponds to this person is 1.25. So they are 1.25 standard deviations above the average height for that class. Now I'm looking at the friend at the same university who's 62 inches tall. So now I'm going to take 62 minus our mean divided by our standard deviation, and that's going to equal negative 0.71. So this one is actually a little shorter than the average person in the class. And now finally, I'm going to say my lab partner is 64.886 inches, and I know that equals the mean that it was provided to me, right? So that means their Z-score is 0. They are exactly the average height for the class, okay? So now let's talk about, general algebra. We know our original formula equals Z equals our raw score minus our mean divided by our standard deviation. So Z equals X minus mu, okay, divided by standard deviation. We can flip that around and we can solve for any one of these variables. We can use algebra. Remember, with algebra, whatever you do on the left side of the equal sign, you also have to do on the right side of the equal sign. So we can flip both things around, all these around, and we can solve for a Z-score if we have the other three components. If we have a Z, a standard deviation, and a mean, I can solve for the X. If I have the, if I'm missing the mean, I can solve for the mean, or I can solve for the standard deviation. I can rearrange the formula so I can solve for anything. Most commonly, you're either calculating a Z-score or you're calculating a raw score that corresponds to a Z-score. So the standard formula for figuring out the raw score is just mu plus the Z times the standard deviation. And that's just basic algebra, okay? So our alternative formula to solve for the X is mu plus my Z-score times my standard deviation. So I'll give you an opportunity to just pause me and then work through a couple learning checks where you're calculating the X value based on data given to you on the other three components. So you're going to use this formula to solve these questions, okay? So you go ahead and do that. And then assuming you're ready, this is our answers. So we have a mean equals 60, standard deviation 5, the X value, find the X value that corresponds to -3 for a Z-score. So I'm going to plug in my 60 here, I'm going to plug in my -3 here, and I'm going to plug in my standard deviation, which is 5 here. And when I do that, it's going to be 6 minus 15. So that's going to equal 45. So my original raw score that corresponds to a -3 Z-score is 45. Makes sense, right? Because our mean is 60, and that means 1 standard deviation below would be 55. 2 standard deviations below would be 50. 3 would be 45. Make sense? Here's our next one. If the mean population height is 64.88 inches, 886, and we have a standard deviation of 4.086. What's the height if your Z-score is 1.79? So we're going to plug in our 64.886. We're going to plug in our Z-score of 1.79. We're going to plug in our standard deviation of 4.086. And we are going to get 72.20. So this person is a little, not just slightly below 2 standard deviations, taller than the rest of the group, okay? And here we have an X value corresponding to a friend with -0.044 Z-score, which means we know they're shorter, not quite a whole inch, or not quite a whole standard deviation, not even quite a half a standard deviation, but they are a little shorter. So we're going to plug in our mean, look at our z-score times our standard deviation, and that's going to tell us that their original raw score, x equals 63.09. Okay, makes sense? If not, when you're doing your reading, it'll start to make sense as you go, okay? So now, let's remember, you can rearrange that formula because there is a relationship between the z and the x and the standard deviation and the mean. There's a relationship between those four components. So if you know 3 of the components, you can always solve for the 4th. So we can solve for standard deviation or we can solve for the mean. I like to use pictures, they help, but not everybody does. So that's completely up to you. But if we're looking at a 65 mean and a 6 standard deviation, well here, this one's a 65 mean, 59x and a negative 2z. So we know that the 59 was the x and that also represents 2 standard deviations. So the distance between 65 and 59 is 6, right? It's 6 points, but that represents 2 standard deviations. So my standard deviation is only 3, okay? It's half of this, okay? Because this includes 2 standard deviations. If I want to look at 6, if I want to look at standard deviation of 6, an x of 33 and a z of 1.5, now it's asking me what's the mean, right? If I know that the 33 is 1.5 standard deviations above, then I know it's 9 points above the mean, because my standard deviation is 6 and this is 1.5, so it would be 6 plus another half of 6, which is 9. So I know it's 9 points above the mean. So if I go back to my picture, it would be 9 points above the mean, right? And it told me my mean was, no, I'm solving for my mean. So I know that 9 points above the mean would be 33. So 33 minus 9 is going to be, what, 24? So my mean would have been 24, okay? So you can, again, you can use a chart or you can plug it in, rearrange your formula, and solve for anything you want, okay? And this is taking you through the mathematics of solving that. So if you want to go ahead and pause me and figure this out mathematically and then come back and look at your answers, okay? Here's your solutions that I just walked you through. Okay. So based upon all of that, we know now we know what a z-score is. We know that the normal distribution has predictable patterns based on the central limit theorem. We know that the mean, median, and mode all line up right in the middle of a normal distribution. And we know that about 70% fall within 1 standard deviation above or below. 95% fall within 2 standard deviations. We know we can use a z-score as a standard means of measuring distance from the mean, and it allows us to make comparisons between 2 different data sets. We know that the z-score itself tells us whether or not the raw score was above or below the mean based on the sign of the score, and the score itself tells us exactly how many standard deviations. We know our formula is x minus the mean divided by standard deviation. So given any raw score in a data set, as long as we know the mean and standard deviation, we can calculate the z-score that corresponds to that score. And that instantly tells us where it lands in the distribution visually. We also know because of algebra that we can rearrange that formula, z equals x minus the mean divided by standard deviation, and we can solve for any one of those 4 things because they all have a distinct relationship to one another, okay? And then this is an important tool because it tells us, you know, it gives us this critical region, that other 5%, to figure out if you are in fact in the critical region. And if so, you're said to be statistically significant, and that'll come back later. So get into the habit of drawing out your normal distribution curve and identifying those critical regions. And we'll talk about that more in the future. For now, I want you to look at the distribution itself. A z-score distribution is in fact a standardized distribution. So every single raw score can be converted to a z-score. All z distributions, the mean equals 0 and the standard deviation equals 1. So they are very predictable. Because they're predictable, we're able to make comparisons between two distributions, even if those original distributions weren't similar to one another. They had completely different means, completely different standard deviations. So when we talk about the characteristics of z-scores or standardized distributions, they always have the shape of the z distribution ends up being the same as the original distribution. So if you have a negatively skewed x distribution, it will convert to a negatively skewed z distribution. Same with positive, okay? But when we talk about z-scores themselves, we're only looking at normal distributions, okay? The mean for a z distribution is always 0, and the standard deviation is always 1. That never fails, okay? And that really gives us a really good anchor to draw conclusions and make comparisons. So we can take any score, any distribution, and convert it to a z distribution or a standardized distribution, right? Like we can take, or excuse me, a standard distribution. So any distribution, we can take any set of scores and transform them to z-scores. We can do it in SPSS with one click, okay? Again, we are going to end up having the distance from the mean to the next block is our standard deviation. And we know that for any set of scores, your mean for your z distribution is always 0 and your standard deviation is always 1. So your z-score at 1 standard deviation is 1, your z-score at 2 standard deviations is 2, and then on the other side, your z-score at 1 below, 1 standard deviation below the mean is going to be -1, z-score 2 standard deviations below the mean is going to be -2. Okay, so when we're talking about using z-scores to make comparisons, I want to see, like, okay, Dave did this, did his psych exam and he got a 60, and how does that compare to the rest of the class when the average was a 50 and the standard deviation was a 10? He also did a bio exam and he got a 56, and the mean is a 48 with the standard deviation of 4. So how do the two scores compare? I can convert Dave's 60 score to a z-score, and I can convert the 56 to a z-score and make a comparison and say which one did he do better on. Just like I can convert yen to pesos, or excuse me, I can convert yen to dollars and pesos to dollars, and now I can compare which one's cheaper and which one's not. So if you pause me and then come back, you can work those out, okay? So here, when we plug all the data in, we use our formula. The psych exam, you take the score of 60 minus the average divided by 10 equals a z-score of 1, okay? So he only did 1 standard deviation above the mean in the psych exam. In the bio, when I plug it all in, he did 2 standard deviations above the mean. That allows me to draw a conclusion. He did better on the bio exam than he did on the psych exam, okay? Okay, so because I have a standard means of comparison, I can draw conclusions now. Now remember I said I was doing approximations. When I said that about 70% fall within 1 and 95 fall within 2. Remember how I said that? Well, now we're going to look at the precise numbers. I've been working on approximations because it's easier mathematically, but now we're going to work on precise ones. So actually here is the actual breakdown of a normal distribution bell curve. where it's not quite 70%, it's actually 68.26%, and it's not quite 95%. I'd have to add all those up. Let me do that. I'm gonna add up this right here, 13.59. Plus, I'm gonna add up this chunk here, which is 34.13, and then another 34.13 here, and then another 13.59 here. So the actual number is 95.44% of the population falls within 2 standard deviations, okay? So these numbers represent the exact percentage of data points that fall between the mean and the 1 standard deviation below, a mean and a z-score of -2, a mean and a z-score of -3, okay? So this is about 50% of all the data. And then if I'm going up, now it's 50% plus another 34.13, which is 84.13, and then plus another 13.59 is 97.70. And so that's 2 standard deviations above the mean. You're in about the 97th percentile, meaning you're higher than 97% of the other scores that have been collected. And now notice between here and here, between 2 and 3 standard deviations, that's just 2.14% of the population, and above 3 is just 0.13%. So if we relate this to IQ, and you have an IQ of 100 is the mean, 115, 130, 145. If your IQ is above 135, or excuse me, 100, 115, 130, 145. 145, you're a freaking genius, right? We actually consider you to be gifted or highly intelligent above 2 standard deviations, but even above that, that's Mensa, okay? Make sense? Okay, let me close out the calendar. There must be some sports games on because you hear my neighbors. Okay, so z-scores are really great because they give us that way to kind of visually see where any score falls within the distribution relative to the mean. And it allows us to compare scores from 2 different distributions. They can be hard, you know, when you're cumbersome, when you're talking about everything in terms of a z-score. Just give me the raw data. But they're valuable because they let us know kind of how scores compare to one another, right? And what we can do is we can also then standardize any score. When you actually test millions of people, the average was not 100 for the IQ, but it's a really easy number to use. So it's just like converting money, right? Where I first convert it, I take my yen and convert it to dollars, and then I take my dollars and convert it to pesos. I can do the same thing if I want to standardize a data set. I can take what my original IQ scores were, and I can convert them to z-score, and then I can say, okay, I want standardized scores that are easier to read and report. And so I'm going to impose a mean of 100 and a mean and a standard deviation of 15, because those are easy numbers to work with. And now I'm going to convert based on the z-scores. I'm going to convert that now to a new raw distribution, a new distribution, standardized distribution with a mean of 100 and a standard deviation of 15. So I converted my yen to dollars, and then from that, I can use my dollars to convert it to pesos. Make sense? That's what we're doing when we're standardizing a distribution, okay? And so if I have a distribution of exam scores where our original mean is 57 and my original standard deviation was 14, and I want to transform it into a new standardized distribution with a mean of 50 and a standard deviation of 10, just for it to make sense or to be easy, then what would my new scores be, right? So if I had 2 raw scores, 64 and 43 in my original distribution, what would they now be in the standardized one? So let me just write this down really quick. And then let's do this together, okay? And what I'm going to do is I'm going to go back to, my whiteboard, and I'm going to clear this all out, okay? And so I'm going to draw now a new distribution, okay? Oh, excuse me, I'm going to go ahead and put that up clear first, up a little further. You'll see why in a second. Okay, so I'm going to do a new distribution. And my original distribution, the mean was 57. So that's 1 standard deviation above and 2 standard deviations above. And I know my standard deviation was 14. So this score would be 57 plus 14, which would be 71. And then this score over here would be 71 plus 14 would be 85. On the other side, 57 minus 14 is going to be 43. And then 43 minus 14 is going to be 29. Okay, so now what I know about z-scores, I'm going to go ahead and I'm going to go ahead and make my z-scores blue. Okay. No, I'm gonna lie. I'm going to make my z-scores green. And reason being is because we're using dollars, right? So I'm going to make my z-score green. So if I convert these to z-scores, I know the 57 is going to become 0 because all z distributions, the mean is 0. I know that my standard deviation becomes 1. So 0 plus 1 at 1 standard deviation is going to be 1. At 2 standard deviations is going to be 2. This is going to be -1, and this is going to be -2. Now, if I want to impose a new standard, a new mean of 50, and a new, oh, excuse me, I'm gonna use a different color so it'll be easier. Okay, so I'm gonna do red because that's gonna be what I'm trying to solve. Okay, so now my new standardized score, I want to have a mean of 50, and I want to have a new standard deviation of 10. So that means this is going to become 60 because it's going to be 50 plus 1 standard deviation is 10, and this is going to be 70, and on the left side, this is going to be 40, and this is going to be 30. So that means in the original data, the 29 raw score, and in my new standardized data, my standardized distribution, the new score would be 30. I converted it from yen to dollars, from dollars to pesos, okay? So my original score that was 43 now becomes 40. My original score that was 57 now becomes 50. My original 71 becomes 60, and my original 85 becomes 70. So it's asking me to say my original raw score was 64 and 43. What would be the new score based on a new distribution, okay? Based on the standardized distribution. Well, I already have 43 right here. I already have it right here, right? So I know the new score now is going to convert to 40. And 64, let me figure out where 64 lands. 64 is going to be somewhere over here, right? So 64 minus my mean is 7 points. So that's only a half of standard deviation, right? So that would equal to a z-score of 0.5. On my new standard distribution down here, a 0.5 z-score would be equal to a 55. So it converts to 55. Make sense? Okay. It's confusing until you, until you do it a lot, okay? That's what your homework's for. So you can have lots and lots of practice and do it again and again and again. So go ahead and pause me, and then, well, you're not gonna pause me because I just worked it out, but if you wanna pause me and then figure out sometime on your own, or figure out how to solve it on your own, that'd be great. Here are solutions, right? You are gonna take the original data, you want to transform it so that here's your new mean and standard deviation, and you figure out your raw scores. You can just plug it into your formula. So you take it and convert it to the z-score, and then based upon the z-score, you now plug it back in to solve for x based on the new parameters of 50 and 10. And that's going to give you 55 and 40, consistent with what we just saw. Okay? Okay. Now, let's look at when we talk about computing scores, z-scores for a sample. It's the same exact formula, okay? Only now, instead of working with mu, we just are working with a mean, right? So we're just using our notation for our samples, statistics, instead of the parameters. So no more Greek letters, only regular alphabet. However, all the same rules apply. You still have a mean of 0, standard deviation of 1. Make sense? Okay. So pay attention to the symbols, because that tells you whether you're working with a sample or a population. At some point, we'll apply a different formula when we're calculating populations compared to samples, just like we did with variance. Remember, the denominator we divided by n for a population, but for a sample, we divided by degrees of freedom, or n minus 1, so that we'd account for that sampling error, okay, that expected difference, that natural difference that occurs between a measurement of a population and a measurement of a sample. So pay attention, because your formulas at some point will be different, okay? So overall, how does this all relate to research, right? Well, we have a population. There's no treatment that's been applied, just as they exist. We randomly sample 100 people to be in our sample. We give them a treatment, and now we look at their score after the treatment, and we want to say, how does their score now compare to the scores originally? We can now look at this new score and say, is it above the mean? Is it below the mean? Is it within the 95% of what normally happens, or is it in that critical region? If it's in that critical region, then that tells us there's something different about that score, and that means that our treatment did something, our treatment worked. If it's not in that critical region and it's just with the 95% of other scores, even after the treatment, then it's no different and the treatment had no effect. It continues to act like the 95% of the population. So what we're doing, we're testing, we're using z-scores to test our hypothesis to see if the treatment did cause our mean scores to fall into a critical region. So if I'm testing out a drug for depression, I want to see, did depression scores go down after the drug? Are those scores now significantly different than what the scores look like for 95% of the other population? Or if I'm looking at happiness, did your scores go up? Are you now happier than 95% of the other population based on my treatment? And typically the marker we're going to start out with is a z-score of 2. If you are above or below, if you're above a z-score of 2 or below a -2, there's something distinct. You are at less than 5% of the population, okay? That makes you significantly different. So that's kind of a peek into how we're gonna use z-scores. You do your homework, do your reading. I love the way this book reads, so hopefully it's easy to understand when you put the lecture together with the book and the learning checks and the homework. You should be good to go on z-score. Let me know if there's any questions. Bye.